All right, let's get started with Chapter 9. So this chapter covers solutions. We're going to kind of truck through it as best we can. I've skipped some things that are more concepts that you just kind of read and you get, but I made sure to include all the math and some of the harder concepts to grasp. So let's get started. The first section in Chapter 9 was on solutions. So there's some vocabulary that's kind of hidden on this first slide. You want to know what a solution is, that it's a homogeneous mixture of two or more substances, and you want to know how they're formed. And the key is that there's sufficient attraction between the solute and solvent molecules. They've got two components, the solvent, which is the larger amount, and the solute, which is the smaller amount. So all of those things on this first slide, you'll need to know. We're going to move a little fast this time, so if you have questions, you need to make sure that you raise your hand. Even if you don't, if you have a question and you're trying to type it out, raise your hand so I know there's a flag on the play, and I'll pause. And then I'll let you get your question in the chat, or you can ask it. Other than that, we're going to move forward. So this slide is from the pre-recorded YouTube video, just trying to give you a little bit of a refresher of what a solute is, and we'll answer some questions. So solutes can be liquids, gases, or solids, spread evenly throughout the solution. And they have the same physical state as the solvent. Let's highlight that part. So when you mix a liquid, a gas, or a solid as a solute in a solvent, they eventually have the same physical state. Okay. You cannot separate a solution by filtration. And solutes are not visible. So those are some of the key characteristics of solutes. So let's try a learning check. These two, let's see, were part of that extra credit assignment. So you have to identify the solute in each of the following solutions. I'll give you a minute to read through these and choose. Based on what you know about what a solute is, it's the smallest part of the solution. So I'll give you a minute to look these over and figure out which one it is. So we'll say that all of the ones on the that are named first we'll call A, named second we'll call B. So we can go over these. Okay. So we're going to go over A, B, and C. But for B and C, that was from the extra credit assignment. So for A, we've got 200 milliliters of oxygen, 800 of nitrogen gas. Yeah, it's going to be the smaller one, right? The 200 mLs of oxygen gas. What about B? Yeah, you already answered B and C. So we've got 5 grams of salt and 200 milliliters of water. 5 grams of salt is pretty small in comparison, so that's going to be the solute. And then we've got 3 milliliters of isopropanol and 8 milliliters of ethanol. 3 milliliters is less, so that's going to be the solute. So the solute is highlighted in yellow. Any questions here? Alrighty. Remember with solutions, like dissolves like. So if you're taking two things and you're trying to combine them, they have to be similar. They're both polar or they're both nonpolar. That's the only way that you're going to have a solution form with a solute and a solvent. So the key here, like dissolves like. If you need to review kind of what is polar versus nonpolar, review chapter 6. So all of those terms, which we're going to come into some things that are ionic as well. Polar, nonpolar, ionic. Look at chapter 6 if those words don't really ring a bell. So knowing that like dissolves like, let's figure out which of these solutes will dissolve in water. So take a second, read it, and let me know which one of these, which there could be more than one, which of these will dissolve in water. D will absolutely dissolve in water. And the reason is that this is a polar molecule. And water is a polar molecule as well. HCl is polar. There's another one that will also dissolve in water, and that's propanol. It's an alcohol, which means that it has an OH group on it. So it is also, it's got a polar bond in there. So this will also dissolve in water. Any kind of alcohol, methanol, propanol, all of those things will dissolve in water. Questions here, or are we ready to move on? Okay. I appreciate the input. Helps things go a little bit more smoothly. Now let's do a question that looks more into why something dissolves in water. So I'm going to give you a minute to read this through and think about what happens when a solid dissolves in water. And I'll give you a little bit of a hint. So LiCl is an ionic compound, which means that when it dissolves, it breaks up into positive and negative ions. Those ions are attracted to something on the water. There's partial positive near the hydrogens and a partial negative charge on the oxygens. So think about how those charges and partial charges might interact. So I'll give you a minute, and this is 2 questions. So for A, you're looking at how the lithium ions are attracted, what are they attracted to? And then in B, what the chloride ions are attracted to. So I'll give you another 30 seconds or so to finish reading the question. Okay. So for A, the lithium ions, they're positively charged. And something that's positively charged is going to be attracted to something that is negatively charged. With B, it's the opposite. The chloride ions are negatively charged. They're going to be attracted to the partial positive. Does that make sense to everybody? Let me know. Yep. Yeah. But we got a no here. Okay, you got it. But the key is opposite charges attract. So if you see a question like that on the exam, pair up the opposites. Good. So that in a nutshell was section 9.1, an introduction to solutions. Then we move into talking about electrolytes and non-electrolytes. Electrolytes are very important for the body. They maintain proper function of your cells and your organs, and they turn on and turn off a lot of different processes in the body. They help with muscle contractions and all kinds of things. So having the right electrolytic balance is key to being healthy. You don't have to do anything for that though. So I don't know if you saw on the news, but there's all this stuff about raw water and real water. I think real water was the most recent one. That's alkaline water, which we're going to talk about pH in chapter 11. But essentially, we're talking about charged particles in your water, and that threw off the electrolytic balance. And that can mess up your liver, can mess up your kidneys. So I believe they're being sued. I don't want to misspeak. So I believe that is the case. But if ever you see anything that says, oh yeah, you need to drink this water that's got ions in it to make your body healthier, please don't, because it can make you very sick. And please don't give it to children. It will make them even worse off than you. So that's a public service announcement. Electrolytes are no joke. You don't want to play around with that. So let's talk about what they actually are, right? So this table summarizes strong and weak electrolytes and non-electrolytes. And these are the three that you need to know. There's examples in here as well. And I'm going to highlight some of those so that you can see what's really important here, because I think the examples will help you on the exam. For strong electrolytes, we're talking about ionic compounds, and we're also talking about strong acids. When they break apart into their different ions. So here's an example. If I had some sodium nitrate solid, and I added water. Here, water is not a reactant, so we just write it above the arrow. What happens is you get aqueous sodium ions and aqueous nitrate ions. That's what that AQ is, aqueous, which means dissolved in water. That's a sample of what one of those dissolution equations looks like, which we're going to be practicing those in just a minute. But I wanted to give you a sample here. For a weak electrolyte, and let me add here strong acids. For a weak electrolyte, we're looking at weak acids. And it'll say that. You won't have to know, okay, this is a strong acid, this is a weak acid. Or it'll tell you that the acid fully dissociates. That means that you're going to form ions. For a weak electrolyte, what you do is you have kind of an equilibrium. We'll use HF. You'll notice that there's two arrows, one going in each direction. You have some of the acid dissolving into water and forming ions. And then some of those ions will say, you know what, I think we like being together more. And they'll reform the acid. That's an example of a weak electrolyte. The last example we're going to do is one for a non-electrolyte. So that's something that doesn't dissolve, or it doesn't dissociate, excuse me. It will dissolve in water, but it will not dissociate. One example would be urea. So you can have solid crystals of urea. You can buy it, actually, like it's a compound that you can buy. It's useful in chemistry and biochemistry in the lab. That's all. The difference is you're going from a solid to something aqueous. Or in the case of a methanol or ethanol, from liquid to aqueous. But there's no ions at all. It's just a change in physical state. So this was a kind of a drive-by overview of strong, weak, and non-electrolytes. Let me know if I can move on and we can do some problems from here. So let me know if you have questions or if you're ready to move on. Okay. So now we're going to do a quick one where we find the reaction that represents a strong electrolyte dissociating in water. So look at all of these and figure out which one could represent a strong electrolyte dissociating in water. And you could put your answer in the chat if you like. What's your question? You don't have to balance these, but they're already balanced if they're written properly. So don't worry about that. What you're looking for is, with a strong electrolyte, what does that mean? That means that you're going to form ions. So you have to look for the one where you've got ions on the product side or the right-hand side of the arrow. So the only one that fits the bill here is going to be C, because we're forming sodium ions and sulfate ions. And we've only got the arrow going in one direction. So that's a strong electrolyte. There are some other examples too that are on here. So letter B and letter D are both examples of non-electrolytes. You're not forming any ions. You're just changing the state from a liquid to aqueous, which means dissolved in water. The top one is a chemical reaction, so that's definitely not dissociating in water. So does that help in terms of seeing the difference between some of these electrolyte types? Okay. So I'll try to include a question kind of like this next week when we do a little bit of Chapter 9 review. Now we're going to do writing formation of solutions. Letter A was the one from the extra credit, and then B and C are new. I'm going to give you a minute or two to try these on your own, and then I'll write out the answers. If you have questions in the meantime, let me know. So for the first one, we've got magnesium chloride, which is a strong electrolyte. You could also identify it as a strong electrolyte because it is an ionic compound. Ionic compounds have a metal and a nonmetal, and that's what this is. If I start with some solid magnesium chloride, and I add water, I'm going to make magnesium ions, and I'm also going to make chloride ions. But I'm not just going to make one. There's a 2 here as a subscript for magnesium chloride, which means I'm going to make 2 chloride ions. Whenever you see a subscript, that becomes the coefficient for that ion. And that is the formation of a solution of magnesium chloride. Again, if the how did I get to the 2 plus charge or the 1 minus charge, if that's a question for you, then you need to go back to chapter 6 because we don't have time to review that. So that's looking at ionic compounds, writing chemical formulas. So that's what you should have put for the extra credit on that one. Partial dissociation of a weak electrolyte, and this is phosphoric acid in water. A weak electrolyte means that you're going to have an equilibrium. And you're also not going to fully dissociate. You're only going to lose one hydrogen, okay? So whenever you see weak electrolyte, think equilibrium with both arrows going in both directions. And you're only going to dissociate one hydrogen. So that one may have been a little bit tricky. But if you see something like that, do you think you could do it on your own, having this example? Okay. Hopefully the answer is yes, you can. So I'm not sure. Mm-hmm. Yeah, so you're going to subtract one hydrogen from here. So we started with H3. We're going to write out one hydrogen here, and then we've only got two left. That's still part of the acid. Okay. So here's the last one. We've got solid sugar in water. Solid sugar, that is a non-electrolyte. When we add water to this, all we're doing is changing the state. We're going from solid sugar to aqueous, which means it's dissolved in water. So let me know if there are questions here or if you're ready to move on. All right. And we're going to keep going. Which I know the pace is a bit fast, but there's so much in Chapter 9. And I want to give you as many practice problems as I can. The next bit in this section was talking about equivalence of electrolytes. So this is the math problem, right? An equivalent is the amount of an electrolyte or an ion that provides 1 mole of electrical charge. Doesn't matter whether it's positive or negative. The charge of positive ions always balances out the negative ions, so you're always going to have equal amounts. And what you'll want to remember from this slide is this equality. It won't be provided for you, but remember your prefixes. M means milli, which means 0.001. So 1 equivalent is equal to 1,000 milliequivalents. Typically, you'll see milliequivalents per liter when you're talking about IV fluids. So that's going to be the kind of question that you see on your exam. This is the question that I put on the extra credit. So if you didn't get a chance to do it, I'm going to give you a couple of minutes to try it, and then I'll go over it. But you've got a patient blood sample that has 98 milliequivalents per liter of the chloride ion. And you have to figure out how many moles of chlorine are in 1.6 liters of blood. I'll give you about 1.5 to 2 minutes to try it out for yourself. That is the right answer. I'm going to show everybody how we get there. So here's our relevant information. The concentration of our ion and the volume. Right now our concentration is in milliequivalents per liter. We need to figure out how many moles, right? Well, 1 equivalent means that you have 1 mole, in this case, of chlorine ions. So we need to get our concentration of ions to equivalents first, and then we can convert that using the volume and what we know about 1 equivalent being equal to 1 mole of ions. So this takes milliequivalents and converts it to equivalents. Then we can take this number and multiply by our volume. What that tells us is the number of moles, or excuse me, the number of equivalents of the chloride ion. And so what you should get here then you take that number because we're not in the right units yet. You have 1 mole of chloride ions for every 1 equivalent. You're not going to put this in your calculator, but I want you to see the math that you're doing and why it makes sense. From there, we need to take into account sig figs. We can only have 2 sig figs here because of our information. We have 2 sig figs in the concentration and 2 in our volume. So that's how you get from milliequivalents per liter to moles of an ion. You'll definitely have a question like this on exam 4. So make sure that you understand how to do it. Let me know if there's questions so far. Just let me know you're still with me, even if you're not, participating per se in terms of writing in the chat and all the things. You lose like half a point. It's really not a big deal. Right? Yeah, on my homeworks, I don't take off a bunch of points for sig figs. What I really want to see is that you understand how to get to the answer. We can worry about sig figs later. And on the exam, it's multiple choice. So chances are, if you can get to the right calculator answer, you'll choose the right answer on the exam. All right. So thanks for your participation. Thanks for letting me know you're with me. We're going to keep on going. Here's a few more practice problems for you with equivalents and moles. So I'll give you about 2 minutes. These are simpler problems to read through, give them a try, and just see where you are. Make sure that you can do it. So I'll check back in about 2 minutes. And this is just as a reminder. Remember that 1 equivalent is equal to 1 mole of ions. So you'll need that for this. We said it on the other slide, but I want to make sure that everybody knows that, and that 1 equivalent is equal to 1,000 milliequivalents. Those two should help you. So if you didn't get to finish these, don't worry about it. In number 1, 1 mole of iron 3 plus. There are how many equivalents? Well, 1 mole of ions is 1 equivalent. Oh, but I tricked my own self. But because we've got a 3 plus charge here, what we're looking at is charge ions, right? There's 3 plus here. So that means that we make 3 moles, 3 equivalents. We're talking about charge here. For 1 mole of iron 3 plus, we make 3 equivalents because we've got a charge of plus 3. So don't fall for that trap. In number 2, in 2.5 moles of sulfate ions, there are how many equivalents? Well, in sulfate, we have 2 equivalents for every 1 mole of sulfate ions because of the charge. So whatever the charge is, that's how many equivalents you make. And I'll write that at the bottom. The charge is equal to the number of equivalents per mole. The charge of the sulfate ion is 2 minus, so we make 2 equivalents for every 1 mole. You multiply that by 2.5 moles, and you get 5 equivalents. The third question. An IV bottle contains sodium chloride. If the sodium concentration is 34 milliequivalents, then the chloride ion concentration, also has to be 34. You can't have a different concentration of positive and negative. They have to equal out. So total positive and total negative ion concentrations are equal. So if you have a solution that has multiple positive ions and only one negative ion, that negative ion has to equal the sum of the concentrations of all of the positive ions. So I'll make sure that we do another question kind of like this when we do our very quick review of Chapter 9. I'd also recommend that you start the homework as well, the Mastering Chemistry. It's on Chapters 9 and 11. It's combined, and it's not due until Sunday, May 2nd. So I'm changing that to give you as much time as possible to do this because you have an exam next week and everything else. But start the homework early and get your questions in during office hours or during class next week. So let me know how we're doing here. Okay. All right. So that was 9.2. Now we're at 9.3. We're looking at solubility here. There's some math with this one, and then there's also solubility rules and how to apply them. This picture is a little bit scary, but if you know anyone in your family who is type 2 diabetic, then they're at risk for developing gout. And gout can lead to, poor circulation and eventually amputation of limbs. So it is a very serious condition. Again, another public service announcement for the community. If you know anyone with type 2 diabetes, if it is not well managed, please make sure that they understand that is a gateway to some very serious health conditions like gout. We're going to talk about what gout is a little bit. It's just when you have the concentration of uric acid really, really high in your blood plasma. So urea is what we excrete when we go to the restroom. If your kidneys aren't functioning well, then you're not going to be getting rid of urea. And instead, it's going to be dissolved in your blood. And it will be dissolved as uric acid. Eventually, you can't dissolve anymore in your blood. It's not super soluble. So, you're going to start forming crystals of uric acid. And that can block your vessels. Very bad news. So with that, we're going to talk about solubility. There's no happy transition to go from gout and it's really dangerous to let's talk about math. There's nothing good there. I got nothing. But make sure you take care of yourself, take care of the people you love. That's all I got. Solubility, we're talking about the maximum amount of solute that dissolves in a specific amount of solvent. For our purposes, we're going to be talking about water. And typically, you're expressing your solubility as the number of grams of solute that you can dissolve in 100 grams of water. Solubility is definitely temperature sensitive. We're not going to talk about that specifically here, but it is in the pre-recorded video. So make sure you understand that concept. When it comes to solutions, we can have saturated solutions and unsaturated solutions. An unsaturated solution is like the one on the left. You can continue to dissolve solute in it. You can keep dissolving more. Once you hit the point of maximum solubility, anything else that you add, you're going to start seeing some of that accumulate on the bottom. So like in this picture on the right where you've got some salt hanging out at the bottom of the beaker, that's what's going to happen with your saturated solution. You can keep adding solvent or solute, but it is not going to dissolve. So to give you a better example with numbers, let's say that we had a compound and its solubility was 50 grams of solute in 100 grams of water. An unsaturated solution might have 30 grams of solute in 100 grams of water. That's an example of an unsaturated solution. It is below the solubility. A saturated solution may have 75 grams of solute for 100 grams of water. With our compound, that's too high. You're going to start seeing some of that solute in the bottom of the beaker. Is that concept clear? Because we're going to use this to answer some questions. So let me know if you're ready. So first, we're going to do a quick learning check to identify a solution as saturated or unsaturated based on the description. So you can write S or US. For letter A, salt disappears when put in water. Is that saturated or unsaturated? It's unsaturated. Remember that unsaturated means that you can keep on adding more. So you're going to add salt, it's going to disappear into the water. That's unsaturated. Now B, sugar added to a cup of water does not disappear, but sits at the bottom of the cup. Is that saturated or unsaturated? This one's saturated. Now, I know about y'all, but that sounds like somebody's making some Kool-Aid. And in my book, that's okay. That's the only time when it's okay to hear that crunch when you're stirring it is when you're making some proper Kool-Aid for the family reunion. That's the only time. I miss that sound, y'all. Ain't no family reunion with the COVID. And I miss it. Oh, I miss it. But that's what I think about every time I do this problem is somebody's Aunt Jackie making the Kool-Aid with the arm flap. You cannot make good Kool-Aid if you don't have that flappy arm. It's just something about that arm and that spoon that makes that Kool-Aid don't taste that way without Aunt Jackie doing that. I don't know what she does. I don't know what's in her arm. I hope one day to gain that power. But it just makes everything so much better. You cannot make macaroni and cheese. You cannot make fried chicken. You cannot make Kool-Aid if you do not have the flap. It gives you powers. That's all. That's just that's my experience. Maybe your experience is different. I'm open. But in my life, it's always been the flappy arm that gives you the best everything. Grits, I never knew grits could taste that way. It's so simple, but that flat. All right. I miss my family, y'all. The vid is getting to everybody. Anyway, hopefully that randomness will help you remember saturated versus unsaturated. That's the goal. Now we're going to do one that has some numbers involved, right? So at 40 degrees Celsius, the solubility of potassium bromide is 80 grams for every 100 grams of water. Identify these solutions as saturated or unsaturated. You don't have to explain anything, but we'll still use the same nomenclature here. Everything that is below 80 grams of potassium bromide in 100 grams of water is going to be soluble, right? So that means it's going to be unsaturated. If you're above that, then it's going to be saturated. So let's look at A. We've got 25 grams added to 50 grams of water. What that would translate to, if I had 100 grams of water, would be 50 grams. So now we can answer the question. Is that 50 grams per 100 grams of water below or above our solubility? It's below. So that means it's going to be unsaturated. We have to do the same thing for all of these. In B, we've got 30 grams in 30 grams of water. So that's about a third, right? So if we had 100 grams of water, it'd be about 3 times this, right? So let's say we just did, it would be 90 grams in 90 grams of water. That's kind of a lot. We said 80 is our max. So this one's going to be saturated. What about C? 80 grams in 200 grams of water. Is that going to be saturated or unsaturated? This is 200 grams of water. So if I had 100 grams of water, it would be half that. So this one is unsaturated. It can be a little bit tricky with these. So you have to make sure that you look at the amount of both the solute and the solvent. The exam is not going to be that tricky. But I did this purposefully to make sure you understand you need to look at both of the numbers and relate it to the solubility that you have. So you may not have 100 grams of water. It may be 50. It may be 30. It may be 200. So always compare and try to get as close to 100 grams of water, and then do the same thing with your solute. So here we divided our amount of water by 2. So I divided the amount of potassium bromide by 2 and got 40. So if we're right at the solubility, we're good. So I'll include some more practice for that next week. The other portion of solubility that we're going to talk about is soluble versus insoluble ionic compounds. You're only going to have a soluble ionic compound if it contains an ion that is soluble. when we're talking about insoluble compounds, the bonds between the metal and nonmetal are so strong that the water can't get up in there and interrupt anything. This box, this table 9.7, these are the solubility rules that you're going to use. I'll go through an example with you on this slide just so that you understand how to use the solubility rules, and then we'll do some more examples. Let's say that I had the question, is magnesium chloride soluble? I look at the two ions that magnesium chloride is comprised of. It would be magnesium 2 plus and Cl minus. Those are the two ions that make up this compound. Then I go to my table and I find where it mentions either one of these. So I don't see anything about magnesium on the table, but I do see a rule about chloride. And ionic compounds with chloride ions are soluble except when they're combined with silver, lead, or mercury 1. I have magnesium, so that's not an exception. The answer to this is yes, it is soluble. What I like to do with this table, so that you don't get confused when you see the exceptions, is I box the exceptions in red. Because red is like angry, no. So everything is soluble except for the things that are in the angry red boxes, right? And then down at the bottom, if you have an ionic compound that doesn't have at least one of the ions in the box, then they're usually insoluble. So let's test out that logic and see how we do. Are there any questions, or do you want to just try some? Let's try some of them. So these are a couple of questions that you might see on an exam. I put the solubility rules here for you. You will have access to those for the exam. You don't need to memorize it. Use these rules to determine which compounds are soluble in both of these questions. I'll give you a couple of minutes and then I'll check back in. So we've got to figure out which of these compounds is soluble in water. Yeah, it's one of my favorites too. One of my favorites. So you know it's hard. I'm sitting here, it's just staring at me like, hey, how you doing? We're just going to sit here and get cold. But that's all right. That's how committed I am to y'all, that I will let my chicken get cold. Cold chicken is just not the same. But for y'all, I'll do it. Because I want y'all to get this. I want everybody to be great. So with the first question, we're looking at sulfates. So copper 2 sulfate, barium sulfate, lead 2 sulfate. The ions we're dealing with here these are all the ions that we're looking at. It's up to you if you want to figure out which ones are not soluble and then, by process of elimination, or if you just want to use the rules to figure out which one is soluble. However you approach the question, it's up to you. I'm going to figure out which ones are soluble and then move from there. So, I find my rule about sulfates. Sulfates, generally soluble, but we've got some exceptions. I'm boxing them in red. Barium 2+ and lead 2+, those are exceptions and they're not soluble. So the only one that is soluble is A. Now we'll move on to the second question. We're still trying to find which compound or compounds are soluble. These are all of the ions that we're interested in. We've got the ammonium ion, which is NH4+, and then we've got zinc and nickel. We're looking at carbonate, CO3. There is no rule for that. So that means that any compound that ends with CO3 2-, it's likely not going to be soluble. But let's look at our positive ions. That's the rule that we're really interested in here. If we have any of these positive ions, then that means that our compound will be soluble. The only one that we see here is the ammonium ion. So that means that A is soluble, ammonium carbonate. All the other ones are insoluble. That's the kind of logic that you have to use to answer these questions. Let me know if you have questions, if you want me to try to give you another couple of examples of what's soluble versus not, or if you're ready to move on. Questions, or are we ready? Okay. Then we're going to do one more that's kind of in a similar vein, but this time we're looking at a double replacement reaction and we're trying to predict the products. So if you feel comfortable and you want to try this problem for yourself, go ahead. Otherwise, I'm going to go through this one with you because it's not just a straight up, look at the solubility rules. For this, we have to predict the products. I'm going to highlight the positive ions. So silver will be in yellow and potassium will be in orange. When you take these two solutions, silver nitrate and potassium carbonate, and mix them together, what you're doing is you're allowing the ions to switch partners. So instead of the silver being partnered with the nitrate, it's now going to be partnered with the carbonate. And that potassium is going to be paired up with the nitrate. The positive ions switch partners. So now we've got silver partnered up with the carbonate, but silver is +1, carbonate is 2-. To balance the charge, we have to have 2 of them. And then we make potassium nitrate. So we make letter A, silver carbonate and potassium nitrate. But we're going to take this one step further. Let's figure out which of these compounds is soluble and which is insoluble. I'm going to look at my chart, see where I find silver or carbonate. I don't see carbonate at all. And silver is only mentioned as exceptions for being insoluble. Since we don't see anything, we don't see any kind of rule with either of these ions, assume that it's insoluble. With potassium nitrate, we can look at our rules. And there are actually 2 rules that cover this. If you have a compound that's got, let me not use red. If you have a compound that has potassium, it's likely that it's soluble. If you have a compound with nitrate, again, very likely that it's soluble. So that's some more practice with using that solubility rule chart. If we're all good here, then we're going to keep pushing to our next topic. Okay, now we're at a crossroads. So we've still got a little ways to go in terms of finishing up class. Let me know if you want to have a break, at which point we will very likely be going up until the last minute of class to get through, all the material and the reminders. Or if you want to just keep going, and then there's a chance that we'll finish maybe 5 to 10 minutes early. So let me know in the chat, break or keep going. All right, everybody, we're back from break. We're going to dig into solution concentrations, and then right after that, dilutions. So this is kind of the math portion of the chapter. We're going to learn some different ways to evaluate the concentration of a solution, and we're going to learn how to use concentration units as conversion factors. I always have to roll through the Rolodex of the different terminology for each of the classes that I teach. So in general, when we're talking about the concentration of a solution, what that means is we're looking at the amount of solute per amount of solution. Remember that solution means we're talking about the solute plus the solvent. The amount of solute may be expressed in grams, milliliters, moles. The amount of solution, however, you're not going to see moles for that, but you could see grams, milliliters, or liters. We're going to go through a few different problem types as a way to go over the different types that you might see on the exam. So this first problem is a mass percent problem. And if you feel confident based on, watching the video, taking notes, etc., to tackle this problem on your own, go for the gold. Otherwise, I'm going to work through these problems and kind of make sure that everybody gets it. We've got a solution that's prepared by mixing 15 grams of sodium carbonate and 235 grams of water. And we have to calculate the mass percent of the solution. Well, what is the mass percent? The mass percent is the mass of the solute divided by the mass of the solution times 100%. That is our mass percent. So if we're going to put in our numbers here, the 15 grams, that's the mass of solute. The mass of the solution is the mass of the solute plus the mass of the solvent. So in this case, that's the 15 grams plus the 235 grams of water. I'll show you what that looks like when we put all the numbers in. I'll write that in purple. The mass of our solute, 15.0 grams. Then we have 15.0 grams plus 235 grams. That's the mass of the solution. And you multiply that by 100%. When you add those two together, the 15 plus the 235, you get 250. And there should be 3 sig figs here with that addition. When you divide 15 by 250 and then multiply by 100, you should get 6%, which is C. I'll give you a minute to kind of let that sink in. And you can let me know if you have any questions or if you're ready to move on. I'll stay here for about 15 or 20 seconds, just in case you're taking notes or you're trying to kind of step through it in your brain. Make sure you got it. Okay, so if there's no questions, we're going to move on to the next problem, and we'll do a different problem type. So here, we have to write some conversion factors. Remember that conversion factors look like fractions. The reason why it matters for us to be able to write conversion factors is because we can use these concentrations as conversion factors in other problems where we maybe need to figure out how much of a particular solute we need to make. Instead of 100 grams of solution, maybe we need to make 200 or 320, right? So that's why we need to be able to write conversion factors. For A, we've got 5.75% volume by volume. That's what this V is, the volume percent. That means that you have 5.75 milliliters of ethanol, which is your solute, in 100 milliliters of solution. The reciprocal would be the second conversion factor. So that's the first one. And again, this is talking about volume percent. Where you have the volume in milliliters of your solute over the volume of your solution, which is usually 100 milliliters if we're talking about converting that to a conversion factor. For B, I'll write that in a different color. We're looking at mass by volume. That's going to have the grams of solute, so that's a mass, over the volume of solution. So we write 4.8 grams of HCl over 100 milliliters of solution. Then we write the reciprocal. Those are two examples of how you write conversion factors from these concentrations. I'll pause here for another few seconds and give you a chance to catch up in your notebook if you need to. Take it in. If you have any questions, let me know. And if you're typing a question out and I'm like moving on, just raise your hand to get me to stop. Doesn't seem like anybody has any questions. So we're going to keep moving through the math. Here are 2 questions from the test bank. Wanted to give you some samples of what you might see on the exam. First question, what is the mass volume percent of a solution prepared from 50 grams of sodium chloride and 150 grams of water? So when we're looking at mass volume percent, what that means, again, is the mass of your solute in grams divided by, the volume of your solution. And once you have that, you multiply by 100%. The volume of your solution is usually in milliliters. Notice that it has 150 grams of water. The density of water is equal to 1 gram per milliliter. So 1 gram of water is the same as saying 1 milliliter of water. That's probably the trickiest part of this whole question. But if you know that, then you can just fill in the information into the formula, which is what we're going to do. Our solute is the sodium chloride. We have 50 grams of that. The volume of the solution is going to be 150 milliliters. We have 150 grams of water. That translates to 150 milliliters in volume. Then you multiply by 100%. You should get B. And with these problems, if you're not able to just kind of go through them right now, which is totally fine, make sure that when you're studying for the test and for the final, that you go back through and make sure that you get the same answer. So you can always just put it into your calculator. Make sure that you're putting it into your calculator correctly, because you may know how to do the problem, but it's just a matter of how to put it into the calculator. And for these types of problems, to be on the safe side, you can use parentheses, and that will make sure that you're dividing the solute by the solution first and then multiplying by 100. It shouldn't really matter, but sometimes calculators are a little bit wonky. So help them out, use parentheses. The second problem, let's tackle that one. We've got rubbing alcohol that is 70% volume by volume isopropyl alcohol. we have to figure out how many milliliters of isopropanol are in 1 pint, which is 473 milliliters. First, we need to talk about volume percent. You have the volume of your solute in milliliters divided by the volume of the solution, which is also in milliliters. And you multiply that by 100% if you're trying to solve for what the volume percent is. What we're given is 70%. And isopropanol is the same thing as isopropyl alcohol. It's just a little bit shorter for me to write. What that translates to is 70 milliliters of isopropanol in 100 milliliters of solution. Now that we have this conversion factor, we can figure out how many milliliters of isopropanol are in a 1 pint container. We have 473 milliliters of solution. We're going to multiply by our conversion factor. Be careful here because you want to make sure you use the correct conversion factor. We're told the amount of solution is 473 milliliters. So we can cancel that out with our unit factor, but you still have that 100 down there. So when you enter this into your calculator, make sure that you do 473 times 70 divided by 100. Don't forget that divided by 100 piece. When you do that, you should get 330 milliliters. How are we doing so far? There's a lot of math there, but hopefully it's not too terrible. So let me know if you're still hanging with me or not. Or if you're like, I don't get this. That's a valid response too. Okay. If you don't have it, that's all right. That's why I encourage you to start the Chapter 9 and 11 homework early. Look at all the Chapter 9 problems. If you have questions, you can let me know. So we also need to look at molarity. Molarity, we're talking about moles again. So Chapter 7, we introduced moles. They're coming back. Molarity, we use a capital M for that, and it's the number of moles of solute per liters of solution. So that is going to be key. You need to remember this. That's not going to be given to you on an equation sheet. So know what molarity is. Now I'll show you how to use it. First, we're going to try finding the molarity of this solution. We've got a volume of 0.225 liters, and we know how many grams of potassium nitrate. Grams do not equal moles, so we have to do a little bit of converting first. Remember that molarity means moles per liter. So we have to first convert the grams of potassium nitrate to moles. Then the second step here is going to be divide the moles by the volume and make sure that that volume is in liters. In this question it is, but in other questions it may be in milliliters. So watch for your units. I'm going to do this first piece in blue. To convert grams to moles, you need the molar mass. With molar mass, all you're going to do is look up potassium, nitrogen, and oxygen. You need to add all of those things up. And when you do that, you get 101.11 grams. If you need a refresher on molar mass, go back to chapter 7. That's where we first introduced molar mass. Now we're going to use that molar mass to convert our grams to moles. We put the grams on the bottom so that we get moles. When you put it into your calculator, you're doing 34.8 divided by the 101.11. And that gets you 0.344 moles. Now we'll do the second part in purple. Take the number of moles and divide by your volume, 0.225 liters. So you should get B for your answer there. I'll pause here for a few seconds. And if there's no questions, I'm just going to move on. I want to make sure that we get through it all. But I also want you to have the opportunity to ask questions if you have them. I'll go through another example of a molarity question. How many grams of aluminum chloride are needed to prepare 125 milliliters of a 0.150 molar solution. Just another variation on what you might see. Relevant information. The chemical formula is going to be helpful. The volume and the concentration. First thing that we're going to do is figure out how many moles of aluminum chloride. In the solution. We don't know that. We have to figure out how many moles we have if we've got this volume at this concentration. The second step is going to be using those moles and the molar mass to convert to grams. Again, if you need the refresher on how to calculate molar mass, go to Chapter 7. Molarity is moles divided by liters. If we multiply by a volume in liters, then that means we should get the number of moles. So let's put in our numbers. If we have 0.150 moles for every 1 liter, and we multiply that by the number of liters of solution, which look, we've got milliliters here. So again, make sure that you're paying attention to your units. We get rid of liters, we're left with moles, and we get 0.0188 moles of aluminum chloride. That's the first step. We don't care about moles, we care about the number of grams we need. There's no scale that's going to tell you how many moles. You have to convert to grams if you want to do anything in the real world. You take the number of moles and you multiply by your conversion factor that has the molar mass. So you need to calculate the molar mass here. So you should get C. I think if you put that in the calculator, you get 2.51 grams, but that's close enough. It's C. So in this one, we used molarity as a conversion factor. That's the key to this problem. So I'll pause here for a second, and if you have any questions, you can let me know. Otherwise, I'll move on in the next few seconds here. Okay. A little bit more math, and then we'll be out of this section. With dilutions and solutions, you'll need this equation. And the premise is always going to be that you have some concentrated solution, you take a little bit of that out, and you add some more water, whatever your solvent is. What's the concentration of the diluted stuff, right? Concentration is C, volume is V. What we're saying here is that the number of moles of solute are the same. So if I have X number of moles from my concentrated solution, I can dilute that down to a larger volume, but I still have the same number of moles. So that's how solutions and dilutions work. Let's do a sample. We've got a volume of hydrochloric acid solution, and we're trying to dilute 25 milliliters of 14% to make that 2%. What I like to do for these is to assign my variables. So the stronger stuff, right, the concentrated stuff, we'll call our initial conditions. So 14% is going to be our C1, our initial concentration. 25 milliliters is going to be V1. The 2% is our final concentration. We're trying to figure out what volume of that we're going to make. Just like I do with the gas laws, I circle the variable that I'm trying to find, and then I rearrange the variables first. So I'm going to divide by C2 on both sides. That means that V2 is equal to V1 times this ratio C1 over C2. Then I can just go to my problem and put in all the right numbers. So V1 is 25 milliliters. C1 is 14%, so I'll just put 14 there, and C2 is 2%. When you're putting this into your calculator, parentheses are your friends. So I would put parentheses here just to make sure. When you do the math, you should get 175 milliliters. So if we're talking about the dilution, that volume should be bigger than the initial volume you started with. So if you got an answer that was like 10 milliliters, that you should say, oh, something's wrong here, and try again. But that's how you use the C1 V1 equals C2 V2. It's always going to be some variant of this question. If there's no questions, I'm going to just keep going. I know sometimes y'all prefer for me to just give you all the samples and do the examples for you, so you have something to look back on when you're doing your homework and you're studying, and that's totally fine. But please do speak up if you have a question. So now we're hitting to the last section of this chapter. Not a lot of sections in the chapter, but it was a very big chapter because each one of these sections was like very full. Full disclosure, we're not going to talk about solutions, colloids, suspensions. I did that in the video. I'm going to focus on the math and some of the other, concepts here that you may have had some questions on when you were taking notes. So we're going to jump to talking about freezing point lowering and boiling point elevation. If you have ever made pasta and you made the mistake of adding salt to the water before it was boiling, you probably noticed that it felt like forever for that water to boil. And you're not 100% wrong. The reason is you added some ions. You added some solute to that water. And that is going to increase or elevate your boiling point. Whenever you add a solute to water, the physical properties change. Vapor pressure decreases above the solution. Your boiling point increases. The freezing point decreases. These types of properties are called colligative properties. They only depend on the concentration of solute particles in the solution. Doesn't matter what they are. It matters how much. And that's what we're going to do some sample problems with today. Calculate the boiling point of a solution containing half a mole of sodium chloride in 1 kilogram of water. Now, in the video, there was a chart that talked about the difference in temperature when you have 1 mole versus 2 mole, 3 moles of solute. For boiling point, you're going to increase your boiling point by 0.86 degrees Celsius for every 1 mole of solute. But the question is, how much solute do we have? We're taking this salt, we're dissolving it in the water. We're forming sodium ions and chloride ions. 1 mole of a solid compound, but we've got 1 mole of sodium ions being formed and 1 mole of chloride ions being formed. So that means that we've got a total of 2 moles of solute. Don't skip this step. You have to figure out how many moles of solute you have. So, now that we know when we dissolve 1 mole of salt in water, we make 2 moles of solute. Now we can figure out how many moles of solute we have in our problem. So what this will give us is the moles of solute. Then we can use this conversion factor at the top where we've got 0.86 degrees Celsius for every 1 mole of solute added. And this will give us the temperature change. When you do all that, 0.5 times 2 gives you 1. 1 times 0.86 is 0.86. But we're not done. This tells you the temperature change. We have to calculate the boiling point. The boiling point of water under normal circumstances is 100 degrees Celsius. We're changing that by 0.86 degrees Celsius. So our new boiling point is 100.86 degrees Celsius. About 101 degrees. Not a huge change, but definitely noticeable. In the YouTube video, I did one where it was freezing point depression. So I wanted to give you one of each that you can reference. Let me know if there are any questions here. Just trying to make sure that I fill out the notes here for you. So you take that temperature change and you add it to the boiling point. We've got a little bit more. This is the last major concept that I wanted to cover. So I'm not going to cover osmosis specifically, but I will talk about the red blood cells because you'll definitely see some questions like this on the exam. Isotonic solution, that means that it's got the same concentration of solute in that solution as the red blood cell. Hypotonic means that the solution is not as concentrated. So that red blood cell is going to absorb water, take in water, to try to balance out the solute concentration on the inside of the cell. Eventually, these cells will swell and burst. That's called hemolysis. If a red blood cell is in hypotonic solution, it will swell and burst. If it's in a hypertonic solution, meaning that there's the concentration of salt or glucose is much higher than what's in the cell, then you're going to have a release of water. It's going to give off a bunch of water to try to balance out the concentrations. And in doing so, it's going to shrink, which is really bad too. And that shrinking is called crenation. You need to know the percentages for an isotonic solution. That's an isotonic solution with regards to red blood cells. You'll need to be able to answer questions about whether a solution is hypotonic or hypertonic and know what would happen to a red blood cell in either situation. So there's no questions here about it per se, but I'm giving you the heads up. You'll see something like that on the exam. That's all for Chapter 9. At least that's what we're going over. Make sure that if you have not watched the video, that you do so. I absolutely did not cover every single topic in Chapter 9 today, but I hit all the major points that I wanted to clarify and give you practice problems on. Next week, you have Exam 4. That's going to be on Chapters 9 and 11. The video for Chapter 11 will be posted pretty late tonight, but it'll be posted tonight. I want you to watch that video and be prepared to do a similar type of thing with Chapter 11 as we did for Chapter 9. So next week, we're just going to go through practice problems, some sample exam questions in preparation for your exam. That exam will be available on Thursday the 22nd. We'll say 5 o'clock, but I usually do it right after class. But 5 o'clock just to give myself a few minutes. And it will be available through Saturday the 24th at 11:59 p.m. Eastern Time. Your final exam. So I don't know what happened when I looked at the schedule the first time. I don't remember if I said it the right thing or not, but this is what it is for your final. Your final exam is on May 3rd, which is Monday. It's the first day of finals week. Okay? So make sure that you have time to do the exam on that day. Don't email me on Monday or on Tuesday or something saying, oh, I missed the exam because I had to work. Not going to fly. You have to have some time in here to do it. You'll need about 2 hours to complete the exam. The exam will be approximately 70 questions. Make sure that you have time to do the final exam on that Monday. And so this, I'm changing. I'm going to give you until Sunday, May 2nd. Just to try to give you some extra time, because I know it's the end of the semester. Everybody's stressed. You got 9 billion projects. Everybody's trying to get you to come into work when you got class. So I want to give you as much time as possible to get that homework in. If you have any questions, this is a good time to do it. Otherwise, we're done for today.